Rotor resistance control of induction motors. Know about what is an induction motor, also known as asynchronous motor, is a commonly used AC electric motor. Induction motor is nothing but an AC electric motor. In an induction motor, the electric current in the rotor needed to produce torque is obtained via electromagnetic induction from the rotating magnetic field of the stator winding. So, the required torque is produced by the electromagnetic induction from the stator winding. The rotor of an induction motor can be full gauge rotor or wound type rotor. So, the rotor can be of two types. They may be of full gauge and wound type. Induction motors are referred to as asynchronous motors because they operate at a speed less than their synchronous speed. First of all, we should know about what is synchronous speed. Synchronous speed is nothing but the speed of the rotating magnetic field. A machine which runs at synchronous speed are called synchronous motors, and the machine which runs less than the synchronous speed are called asynchronous motor. Induction motors comes under the category of asynchronous motor because they run at a speed lesser than the synchronous speed, so they are called asynchronous motor. Next, we are going to see about the speed control of induction motor. Speed control of induction motor can be obtained in three ways. We can either change frequency or change the number of poles or change the slip. In the category changing of slip, there are further three types. They are rotor circuit resistance control, stator voltage control, rotor voltage injection. Among these three types, we are going to see about the rotor circuit resistance control. Rotor resistance control. From the basic torque equation of induction motor, we know that torque is directly proportional to S into V1 square by R2. Here S is slip, V1 is the input supply voltage, and R2 is the rotor resistance. In order to maintain torque constant, let us assume that the supply voltage V1 be constant. So the only possible variable is R2. We are going to increase the R2. In order to maintain the torque constant, the slip S will also increase. From that, we can say that for a constant torque, the slip is directly proportional to the rotor resistance. If the resistance in the rotor circuit is increased, the slip is increased and the speed of the rotor is decreased. We can say that the resistance is inversely proportional to the speed of the rotor. If we increase the resistance, the speed of the rotor gets decreased. If we decrease the resistance, the speed of the rotor gets increased. This is the basic concept. The conventional rotor resistance control has some drawbacks. They are listed below. The first one is the rheostat, which is used to vary the resistance per phase, causes unbalancing in rotor. The rheostat can create unbalancing in rotor. This is one of the drawbacks. Then the resistances generate huge losses and generate heat in the system. We are going to use a resistance to control the speed. That resistance can generate some losses, and by that losses there may be generation of heat in the circuit which may cause damage to the circuit. In case of a large machine, size of the rheostat will be large, and in such case it is not easily portable. If we are going to use a large machine, we have to buy a large rheostat for that. In such case, it is not easily portable. This is one of the drawbacks. It requires more maintenance, and hence the cost associated with it is more. We are using resistance in rotor resistance control, so it requires large maintenance. For that maintenance, we have to spend some cost, so the overall cost of the circuit may increase. This method cannot be used for industrial automation purpose, since we have to change manually the value of the resistance. Here, the value of the resistance is changed manually, hence it is not suitable for industrial automation purpose. These are the drawbacks of conventional rotor resistance control method of induction motor drive. Static rotor resistance control. Rotor resistance can be varied steplessly using static rotor resistance control. The main advantage of this method is we can vary the rotor resistance steplessly. There are further advantages which are listed below. They are simplicity of operation using closed loop control. By using closed loop control, the operation can be very simple, and smooth variations of rotor resistance. We can vary the rotor resistance in a smoother manner, which will vary the speed of the induction motor. Quick response of system. The response of the system is very quick. This is one of the advantage, and rotor resistance unbalanced can be eliminated using power electronic devices. Here, one of the drawbacks is in conventional method is unbalancing in rotor. Here, the unbalance can be eliminated by using power electronic devices. We can simply say static rotor resistance control is we are going to use a power electronic device to control the resistance of the induction motor. By controlling that, we can be able to change the speed of the induction motor. This is the circuit diagram for the static rotor resistance control of induction motor. In this, there is an induction motor. The rotor of the induction motor is connected to the diode rectifier and to the resistor and to the thyristor. The AC output voltage of the rotor is rectified by diode bridge rectifier and fed parallel combination of resistor or semiconductor switching transistor PR. Here, the rotor of the induction motor is connected to a diode rectifier and it rectifies the AC output voltage of the rotor, and it is connected to resistor and a thyristor. The effective value of resistance across terminal A and B such that RAB is varied by varying duty cycle of the transistor TR, which in turn varies the resistance of the rotor circuit. Here, we are going to vary the duty cycle of the transistor TR so that the resistance can be varied. So simply by varying this, we can able to control the resistance, and by varying the resistance, we can able to control the speed of the induction motor. In this way, the speed control of the induction motor is done. Inductance is added to the circuit to reduce the ripple and discontinuity in the DC link current. Here, an inductance is added so that it reduces the ripples in the DC current. The RMS value of the current will be IR is equal to √2/3 ID. Resistance between A and B terminal will be 0 when the transistor is on, and it will be R when it is off. When the transistor is turned on, the entire voltage will be appear across the transistor. So the resistance R has no value. When the transistor is open circuit, that is, it is switched off, the entire voltage will appear across the resistance R. So the resistance R has value. And by varying the duty cycle of the transistor TR, we are able to control the resistance, and by varying the resistance, we are able to control the speed of the induction motor. Therefore, average value of resistance between the terminals is given by RAB is equal to 1 minus delta into R. The delta is nothing but the duty cycle of the transistor. We are going to vary the duty cycle by which the resistance can be varied, and so the speed of the induction motor can also be varied and can be controlled. This method of speed controlling of induction motor using this technology is efficient. Comparing to the conventional rotor resistance method, this static rotor resistance method is efficient. We are using resistance to control the speed of the motor. Here also resistive losses occurs. Since we are using resistance in the static rotor resistance control, here also resistive losses occurs, and it causes some unnecessary heating effect on the motor and also reduce the efficiency in some extent, not so much as conventional rotor resistance method, but in some extent. It cannot be operated for continuous operation. It is used in the intermittent application such as overheat planes, load fluctuations, etc. These are the applications of induction motors for static rotor resistance control. Thank you.